Who designed this series of lectures? We've been like doing like robot music for like 3 weeks, and now we're finally at the very end getting to neural speech synthesis. We're like, yeah, 2 days left. But anyway, that's what we're gonna do. Phoebe was gonna talk about neural speech synthesis today, but she's out sick. So instead, you're stuck with me, sort of obliquely talking about it. I want to thank Phoebe and Natalie for helping with the slides today. But this one's interesting because I actually was, Gridspace existed, when this all happened. So this is something where I actually can talk to what happened. So this is where we are. We moved this to today, to Wednesday, and then we're going to do Tacotron tomorrow. It's going to be Ulokman, right? And then Nick is going to take us through the end with variational models up through VITs, and then we will be done, and IAP will be over for the year, and we can all move on to our either semesters or normal life, except for Natalie has offered to maybe do a February IAP, and she just mentioned it earlier.
Every day in February.
Yeah. Can you imagine like Sisyphus, but he just has to like run like MIT lecture series? All right, here's the outline. God, it's like, God damn it, what the hell were we doing? We're just messing around with sine waves for weeks. It's because that's the thing. We 2 years ago when we did our first IAP series, I was talking about, like, why didn't we just like put like transformers in block letters and be like, that's it, we're done. So we had to earn it this time, but it's always where it ends up. Finally. This is a map of the migration of tribes of Polynesia. In general, the Polynesian and Micronesian diaspora managed to very slowly but methodically in small boats over hundreds of years make their way, you can see, from Samoa to Fiji, Tonga, eventually further across the Pacific, and they eventually, even made their way to like Hawaii and Easter Island. Has anyone seen Moana? Yeah, so like that. We're talking about that. So the Moana thing is interesting because they were in very small boats, and the Pacific was deep, big, rough, blue water, and yet slowly but surely, island to island to island, they were able to traverse the Pacific Ocean, and then actually there's a lot of evidence that some Polynesian islands were actually resettled by different groups multiple times. Actually, New Zealand was the last settled part of the planet for the most part. Why am I talking about this? I guess Cooper said explain myself. So you could, if you wanted to build a neural speech synthesis, or you want to build a speech synthesis. We talked about, so we've had nominally a couple lectures on speech synthesis, but really we had some early titans. So we had Gene France, Sandy Disner talking about the early history of speech synthesis. And we also talked about some of the kind of wilder, very early electromechanical and mechanical methods for speech synthesis. And then Phoebe talked about concatenative and parametric methods for speech synthesis, right? Where you just concatenate together phonemes, or maybe through modulation of various parameters can start to more intelligently build speech synthesis. This is how speech synthesis worked for decades, right? But nominally, these different methods, they often split the problem into subproblems. Similarly, we could, like these Polynesians, we could split this into subproblems. And from island to island to island, if with a very small boat, you can get pretty far. By contrast, this is a 16th century Portuguese war and merchant ship. These were the first beefcake blue water sailing vessels, and these could just plow across the Pacific Ocean if they want, and they did, and they made it to Japan from across South America, and you could just do it directly. And the question today is, okay, we start to see the emergence of deep learning around 2012. Neural speech synthesis does not exist. It does not exist in any form. but it's on everyone's mind, as is neural speech recognition. 2012 was the first neuroacoustic model, as is neural machine translation, which you saw, between deep Boltzmann machines and later the first paper on the attention mechanism. You see people trying to attack these various old problems through the neural lens. But there's still this problem of, do we want to be the Polynesians or do we want to be the Portuguese? And that's going to, Cooper loves that. Do we want to be the Polynesians or do we want to be the Portuguese? That's a good question. So, all right, 3 stories. So this Gridspace existed when these stories happened. I remember, in general, the discourse around them. Story 1. So we're talking about sequences. Neural networks are interesting because before deep learning, let's say again, 10 to 15 years ago, state of the art of machine learning was typically applied through the process of experts vectorizing feature vectors through maybe a large amount of human input, and then putting it into one of various convex optimizers, something like a support, or even other optimization methods, from a support vector machine to random forest, various different machine learning methods. And in general, the biggest problem and the biggest motivator for deep learning was the curse of dimensionality, which is as you start operating on larger and larger higher dimensional data, without some sort of automatic feature discovery, through layers of abstraction, it's really, really hard to do hard things like speech recognition, like machine translation, like language modeling, and like speech synthesis. And so we started very rapidly in a very short period of time making progress at attacking the curse of dimensionality through deep learning and its immediate predecessors. This is the MLP, the OG neural network, the multi-layer perceptron, right? And a neural network like this has the ability to model small nonlinear functions. It's not going to do speech synthesis. I'm sorry, but it can start to do things that are somewhat nonlinear in an entirely learned manner. Early neural networks, for many decades, people didn't even really have a good method to train them. You could use, genetic algorithms. You could use other methods for training them, but no one really had a great way to train very large networks until about the 1980s, when you started to see the use of gradient methods to maybe optimize things that sort of look like neural networks. Later on, for operating on sequences, the first method that we really had was the recurrent neural network, where a fixed set of parameters are used repeatedly on the sequence without changing the parameters. This allowed us to operate on a sequence of data, but it allowed us to operate on a sequence of data where at least one side of it had some sort of fixed size or structure. So if you think about speech recognition, or you think about speech synthesis, or you think about any sort of decoding algorithm, or where you have one, different length input and output sequences, and 2, you traverse through the sequences at different rates. That is a very hard problem. Recurrent neural networks, it turns out, and we knew this when they were first invented, are not very appropriate for these sorts of problems. And if you go into the history of optimal coding and control theory and information theory, this is a problem that existed in radio transmission, and there were things like the Viterbi algorithm and other methods for decoding sequences, where not only were the symbols coming in at different rates on the input and output side, like with speech recognition or speech synthesis, but also they are not necessarily being traversed at the same speed. Recurrent neural networks can really only generate inputs in lockstep with outputs. Whereas, you might have a word that's very long, like rough, that is very short pronounced. Or you might have a word that's very short that is very long when pronounced. And you have the same problem in speech recognition. You have the same problem with machine translation. Not to mention that things might not actually be aligned linearly, although in speech synthesis, we're going to assume to first order that they more or less are monotonically progressing through the text. We're not there yet. There were early suggestions for how to do neural sequence modeling. But one of the first solutions was, okay, this is a square peg round hole, right? So you have like different output input sequences. How do you deal with that? This is Seq2seq. I never had been able to pronounce his name right, but he was one of the founders of OpenAI later on, obviously a titan of AI, was the first author on the original Seq2seq paper. So Seq2seq was at least a solution for how do you have a sequence in and a sequence out. Doesn't necessarily solve all of these problems, and there were other things like Alex Gray's transducer and other solutions to try to address these sorts of problems. But the main idea is an encoder-decoder architecture where you encode the input sequence, get some sort of latent space. I think we have a better representation here. I think Phoebe made this. And then a decoder that's able to get to the output. What's good about this is that we now are somewhat agnostic to the length of the input sequence relative to the output sequence. The thing that's bad about it is that there's not really any mechanism to correlate what's relevant on the input and the output. In general, whether it's speech synthesis, ASR, or machine translation, generally a very small piece of the input is relevant to a piece of the output. And as was kind of discussed in the transducer paper, there's also problems where you might want to be slowly stepping through the input or output at different rates. And, in this case, you're still basically fully encoding the input and then fully generating the output. By the way, any questions? Do we have any questions from people? There's like MIT, any questions? Boys section, girls section. Okay, good. Great. This is the original Seq2seq paper. This is the original attention paper. So this was a machine translation paper that introduced the attention mechanism. So this was a way to start to get a Seq2seq model to focus on portions on the input and output. And when Lokman talks about Tacotron, we'll be getting to probably a lot more detail on attention mechanisms. But again, what I'm talking about is story one, is we had folks like this guy trying to deal with sequences. Now think about this is the first 2 years of the deep learning boom, 2012 through 2014. One of the obvious problems, Alex Graves' papers started in 2012, 2010, was, okay, even if we have recurrent neural networks, how are we going to deal with sequences if we want to attack things like speech synthesis? Problem 2, generative models. Speech recognition, classifiers, like ImageNet, ConvNets. A lot of the early deep learning models tended to be models that were doing some sort of classification or regression problem, where most typically the input dimension was much larger than the output dimension. So even in the case of speech recognition, the dimensionality of, maybe 2,000, 3,000 samples or more, maybe as many as 32,000 samples of speech that you then need to decode to a couple tokens, you have a much larger dimensionality of your input space than your output space in terms of the number of bits or the amount of information contained in the input versus the output space. This is just a fancy way to say it's become a bit of it's in the common vernacular to talk about generative AI. Something I've talked about in other Gridspace videos before is, in general, it's a blurry definition because technically every machine learning model by definition is trying to predict something, which is a missing label that it is generating. So all models are a little bit generative. Generally, if you think of a scale and on the scales represent the amount of bits in the input versus the output space, if you have small input, big output, the model is leaning generative. Now, there's a way to cheat. You can make any model generate something of infinite dimension through autoregression, which means you predict something that can be used to seed the same model to generate something again. And you can run that process indefinitely by just extending the tail. The output of one thing becomes the input of the same model again. That is how most large language models are still decoding, or something that looks very close to autoregressive generation. So the question is, how are we going to generate something like speech from something small like a few pieces of text? We had VAEs, variational autoencoders. This was a way, one of the early days of neural networks, like 2012-ish, you had people like Andrew Ng looking at like, how do you build latent spaces? That means just a fancy way for a hidden space that encodes something about what you're trying to generate so that you can control something like, in this case, this is from the original VAE paper. This is like the manifold or the space of faces in the face of MNIST data. And so the idea here is that you have this latent space that is very efficiently using its latent space, and it maps relatively well to the relative distribution of the features that you care about. So for instance, if it's a model like on the one on the right that is generating written digits from MNIST, that you would relatively evenly spread throughout the space the different digits in the MNIST set, and then you'd be able to, traverse that space somewhat smoothly by putting in basically variational loss or statistical loss that is able to enforce that in your latent space. This is one way to do a generative model using a VAE. It's not very efficient. They're a little bit squirrely, but that was one way that we were approaching it. And then there's this guy. So this is Ian Goodfellow. You know Ian Goodfellow. So he was our year in college. He's the inventor of the GAN. The GAN was this first idea of, okay, forget autoregressive generation. We want to make neural networks generate big things like audio and pictures. And we want them to not be bad. And, maybe it makes sense, like autoregression, to iterate. Okay, but do we want to iterate sample by sample or word by word? Or can we maybe make the iterations a little bit bigger steps? And so his approach was, this is the GAN loss. And so basically the idea is that you had two types of loss, one from a discriminator and one from a data generator. And the idea was that one part of the model is trying to generate data, and then another part of the model is trying to predict if it's fake or real, right? And so if you haven't seen a GAN before, GANs were this incredibly clever and original idea where one model is rewarded for finding imposters, and you're laughing, yeah. And one model was rewarded for generating things that looked good, right? So you're trying to fool the discriminator, and the discriminator is trying to catch you trying to fool it. And if you ran this as one flow-based model, you could train these things jointly. And but notably, you had a step towards generating something that was realistic, where you didn't necessarily need to do things autoregressively, but you could still do things iteratively. And later on, so 2 years later, you had Deep Dream, which was a Google paper where you started to see intentional hallucinations from some latent space, where you get these kind of crazy images that at the time were the highest resolution kind of neural generated images that we had seen. And a lot of them were pretty mind-boggling at the time that they came out of a computer. Still no audio. A few years later, 2016, we had GLOW. GLOW was a paper out of OpenAI. It was one of their first big papers. And GLOW was our first foray into using flow-based models. So the main idea was, okay, again, we want to be able to iteratively do something like generate audio, generate images, but we don't want the iteration to just be like one pixel. And so instead, the idea was have some sort of invertible matrix that you learn. And the invertible matrix, it's very easy to take something that looks good and turn it into crap. Trust me. But it's very hard to take some noise and turn it into something that looks good, right? And so the idea was learn an invertible method that iteratively changes maybe a noisy image slightly more into slightly closer to a less noisy image, and by just basically trying to predict going the other direction and then invert it. GLOW was a really, really cool paper that later inspired WaveGLOW, which is one of several models that were later used for vocoders, where again, you're basically trying to invert a spectrogram into samples, right? You can generate spectrograms from samples very easily using the Fourier transform and the algorithms for MEL spectrograms we talked about earlier in this class, maybe. I don't know. I don't remember what we talked about. But we could have talked about that, maybe. Sounds like something maybe you or me talked about. Did we talk about MEL spectrograms? Okay, so Natalie talked about it. That's why no one remembers. And so I didn't make any jokes about the imposter detector. So it's fair. All right, I'm sorry. We have a way to now iteratively generate an image, or then in this case, samples from a spectrogram. But where the iterations are not just like one pixel, one sample. So we're starting to see VAEs, obviously the Boltzmann approach to generative models. Did I thought I have? And I got rid of it, I guess. And then we start to later see things, other approaches like flow-based models and GLOW, where it's like, wow, we can start to generate something that's pretty high dimension, where we don't have to do it sample by sample. But notably, we still don't have a full story for how we can do things like the Polynesians, right? We have pieces of the puzzle, but we don't have something that sounds like sound that was made by a neural network. All right, big deep learning. All right, here we are, Boltzmann machines. So Boltzmann machines, which actually was like partially the winner of the Nobel Prize this year. The idea here was a very early precursor to the neural network that was inspired by statistical mechanics and physics. And from the beginning, these models were generative. They were intended to be generative, and whether the generation was predicting a label or was predicting something from the sample distribution, these were essentially thermodynamic machines that were an early precursor to neural networks. And then deep Boltzmann machines, where you started to see, again, around 2010, 2012, the first examples of layered abstractions being learned fully, albeit very slowly. You started to see, okay, if we just made things really big and we were really patient and we had a lot of compute, we could start to analyze really big problems. So there's, again, another Nobel laureate for machine learning, Demi Hassabis, who founded DeepMind. A lot of the original approach was scaling up deep learning to things like reinforcement learning problem, games, but also just trying to take advantage of just a huge amount of resources raised by that company to start to just solve some big problems using deep learning. And they were really the first, before OpenAI, before anyone else, that was just trying to scale up compute for deep learning at the beginning of this era. And one of the first big wins was WaveNet. So WaveNet, this is the decoding algorithm here, which is just basically any statistical prediction of a sequence looks like this, which is try to predict a sample from the next samples, right? And the big idea was, what if we used a lot of computers? And what if we didn't care if it was really slow? Could we just force feed a big autoregressive model to generate something that sounded really good? And so, one idea here was you could just do it where every single sample was in the causal flow for every other sample. So that's, kind of what this is, right? Like, so my sample, T, is conditioned on every other sample before it. And they did this at 16,000 samples per second. So if you wanted to generate 10 seconds of audio, that would be 16,000 samples. And, with a, bit depth of 16, you would have 2 to the 16 things on your softmax that need to be predicted on the input of maybe 160,000 of those things. So that's a really, really big neural network. Too big even when your strategy is like, what if we just used a lot of computers? So they did do something, which was they did something kind of like a ConvNet, which is, they call it a dilated causal convolutional layer. It just means it's like a comb, that it's like, okay, what if we just don't use every single sample, but we use a mix of samples and we use layers to essentially kind of smooth out how much flows from each to the X. So basically this output layer is technically dependent on every other sample, but really is looking at blocks of samples causally. And this was a way to try to make it so that the model wasn't quite as overburdened trying to do this problem. This is what it looks like. At the end was a softmax out of all the possible sample values. It wasn't a regression problem. It was literally trying to classify what sample bit pattern for each sample. So, it treated, 2 values that were very close together, or 2 values that were very far apart as just different classes. And, it took in basically this causal comb repeated, like we just saw on the last slide, and then basically tried to predict from that what sample comes next. And this was a really brute force approach. It was like driving a cement truck through the bank, and it worked. There were problems, but we'll get to those in a second. So we talked about, or Phoebe talked about in the last lecture, some of the earlier approaches. These are the original two examples from the DeepMind site when they revealed WaveNet in 2016. So this is a parametric model. So I'm just going to play all the models in a row, right? So here's parametric.
Aspects of the sublime in English poetry and painting, 1770 to 1850.
And this was probably about state of the art at the time. So here's a concatenative example, same phrases.
The Blue Lagoon is a 1980 American romance
and adventure film directed by Randall Kleiser.
Aspects of the sublime in English poetry and painting,
1770 to 1850.
And here's the first neural speech synthesis model.
The Blue Lagoon is a 1980 American
Romance and adventure film directed by Randall Kleiser.
Aspects of the sublime in English poetry and painting, 1770 to 1850.
So to my ears, this still sounds pretty close to perfect. And at this point, it's nearly a decade old. Problem, it was incredibly slow. This is from the paper. Natalie, thank you for finding this quote. I knew there was some quote in the paper. So it's like, WaveNet relies on sequential generation of one audio sample at a time. It is poorly suited to today's massively parallel computers and is therefore hard to deploy in real-time production setting. We're talking many hours to produce like a second of audio. There's a real-time factor of tens of thousands, hundreds of thousands. So that was the trade-off. You know, the monkey's paw was you got to have, neural speech synthesis that sounded perfect, but it was computationally intractable and you treated it like a scientific computing problem, that was the mission, right? Like, let's solve, this big computing problem with neural networks. And then later on, us or someone else will figure out how to make this good enough for something like, Grace at Gridspace. Okay, so we could maybe start to make it fast. So this was actually from DeepMind. Parallel WaveNet was their first crack at trying to make this computationally tractable. So what they focused on is what's called student-teacher distillation. The idea is that you have your now really good WaveNet model, and you try to train a smaller student model to reproduce the generating process from your parent. So it's a form of distillation, and in general, the causal structure of the student allowed it to essentially be parallelized. So it did, and so this was an approach, kind of complicated, didn't work that great. There was also Wave RNN. This was another approach to parallelizing it. There were a couple other approaches. In fact, there was a flurry of people. People were very excited. This is, we went from the neural speech synthesis was postulated but did not exist to it existed and it sounded perfect. And all we needed to do was make it fast to make it tractable. And the last 10 years has been that journey. These first couple approaches that came in the flurry in the next 2 years were very imperfect and were not that great. But they were the logical next step. And so we ended up in two tribes. I guess the Portuguese and the Polynesians, is that right, Cooper? The Polynesians and the Portuguese. Tribe one was end-to-end. Maybe just go direct, be the Portuguese. They have a big ship that just crosses blue water. And we just need to, make WaveNet fast, and we got that ship. Tribe 2 was break WaveNet up into those little archipelagos, into lots of little substeps. That is what we've been doing for years with earlier speech synthesis methods. And that goes from generating linguistic features from graphemes to generating phonemes from these linguistic features, generating spectra or acoustic features, and then finally vocoding it into samples. The smaller the subproblems are, the more specific the task of the smaller model, the lower the variance in the generating process that maybe needs to explore, the more tractable that you could do. And maybe let's try to get rid of autoregression. Although really everybody wanted to get rid of autoregression. So these are the two approaches. These are the two boats we could ride. This is essentially how things played out, right? This huge amount of excitement about deep learning. 2-3 years later, WaveNet comes out. People see proof that neural speech synthesis can sound perfect, and it was just a matter of how to make it tractable, which has been the last maybe 8 years. I wish I could tell you that it was a really easy, neat debate, but I would say that this battle is still ongoing today, which brings us to Tacotron. Because, so next week, tomorrow, Lopan's going to be talking about Tacotron. Tacotron is a Seq2seq model. It's an attention model. It's a model that relies on breaking the problem into subproblems. It's the Polynesian approach. And it leaves open a selection of vocoder, which opened the door for many different approaches for neural vocoders. The process of, in that case, inverting a spectrogram. And Lopan's going to get into the details of it. And so that's the early history of neural speech synthesis as I remember it. Unfortunately, Phoebe had like all these slides. I didn't show them, but they were very good. But I kind of thought I wanted to tell these stories because this is how it happened, and the why is, I think, because we don't use any of this. The why is more interesting than the what. Similarly, I think that was true with parametric and concatenative as well, which is they're historically interesting because they help explain why we have the models we have today. But starting tomorrow, we're talking about models that are still used today, and model architectures and approaches. Does anyone have any questions?
What exactly was the WaveNet?
So let's go to a picture of WaveNet.
It's TTS, right?
Yeah, it's a TTS model. That's right. And WaveNet. Do we not have a picture of the model? Yeah, here we are. Was this input? Does this answer your question? Input. I believe it was characters, but I can't remember exactly. But I think WaveNet, the goal was to just show general neural sound generation. So there were a lot of follow-up papers that were looking at other things than speech synthesis, but I'm pretty sure they just encoded characters. But it was not a Seq2seq model. That's what you're asking. Other questions about any of these models? I talked about them fast. By the way, I was telling Natalie earlier, the GLOW paper, which was very influential in later flow-based models, really, really cool paper, really original. Obviously, some of these other papers are really interesting too. WaveNet paper is very simple, right? Like again, very brute force approach. But some of these, early approaches to try to make things tractable were really original, creative, and are still very important today. Like in general with generative models, there's around 4-ish general approaches that have emerged over the last decade, right? So you have things like VAEs and other autoencoder approaches, which have these really nice latent spaces. You have flow-based models that focus on this idea of kind of reversibility. You have diffusion-based models that instead of looking at flow, look at a diffusion process, which is non-reversible, and you try to, again, make it reversible. And then there's autoregressive approaches, right? This is like our tool chest for generating things like audio, like text. In the case of speech synthesis, it looks very different in terms of the dimensions of the input-output space, and also how much you can precondition the input to be a better one-to-one mapping on what's going to be synthesized, right? We know that English spelling does not map perfectly onto pronunciation, but we do have the ability to look up the pronunciation in terms of phonemes or the IPA spelling or a simplified version of the IPA spelling. And so we can already, without doing any modeling, try to get the input space into a better format. And then obviously we also know, so in the case of spectrogram generation, we can go from that point forward, we know how to go one direction perfectly without a model at all. So we can try to chip away at the problem so the portion that maybe needs a model for the generating process is the most mysterious portion, right? And so that's a lot of the Polynesian argument. Other questions, comments? Is there anything that people are excited about? No. Has anyone had any interesting dreams? Has anyone been deep dreaming? I had a dream the other day, and it was a terrifying dream. I swear to God, it was this building here. And I remembered it as soon as I saw this paper. I'm like, that was my dream. I dream of it every night since before the paper was written. Any other questions about where we're going, about what's left? There's only 2 lectures left. And they're the ones where we end with modern speech synthesis. So again, Tacotron, Polynesian, Wits, a little bit more Portuguese.
Let's talk about the last several years of advancements that we've seen in large language models, seen any sort of reflected improvement also in large speech voice generation.
Oh, that's a really interesting idea. So Griffin's asking, can we maybe, once we get through Wits, talk about, tell me if I'm repeating this right, but is there anything that we can borrow from all the progress in large language models?
We just keep doing lectures when we go further and further into the future.
Yeah. Lecture 13, we're talking about unreleased research. So, I'll tell you what, one way to look at the causal tree is all these things use transformers, right? Which we haven't talked about much in this class, but we've talked about in past things. And so they've all inherited the successor of the attention model, which was just remove everything else, right? And then do that a lot, right? And so, transformers, like we talked about in the first IAP series 2 years ago, were the solution to the problem of how do we make attention models really big and parallel as well, so we can make them even bigger, so we can train them on the whole internet or all of with DeviantArt. I don't know, what do they use to train Dolly? I don't know. This is all Sanix. Yeah, Newgrounds use to train Dolly. And so, so they're obviously all inheritors of transformers. But that said, I think, that would be a really interesting thing to talk about. There's a large amount of research on neural speech synthesis now. At the time, there's just a lot of hand wringing about someone was going to figure it out, and it took lots of just money to just make a big expensive model. But it sounds great. But yeah, I also think that language modeling at its heart is not really that generative, right? It's predicting one token at a time is actually a fairly myopic classification problem. You see, essentially WaveNet is the language modeling approach, which is autoregressively predicting one sample at a time. The bit depth of a audio wave and the lexicon of a typical language model is relatively same order of magnitude, like 10 to the 5, 10 to the 6, 10 to the 7, right? And so you can kind of think about, that is the language modeling approach. Which is, it didn't use transformers, but you could have a transformer that then predicted one sample at a time. And I'm sure people have done that. But I would say that right now, you look at the last 5 years of generative models, generative AI, there's, autoregressive models like, GPT. There's variational models. There's diffusion models. There's flow-based models. That's anything where you have to have a big big output dimension. That's been the 4 camps. But that said, I think there's a lot we can talk about in terms of just the interplay between language modeling and TTS for sure. Or I guess Nick, you can talk about that. He's going to be lecturing. I wasn't even supposed to lecture today. I wasn't even going to work today. It's Wednesday. Here we go. It's Wednesday. Wednesday's my least favorite day, and so I don't know if you guys noticed. I'm never here on Wednesday. I do the Home Alone thing where, that's hot tub day for me and Nico. I do the Home Alone thing where there's 2 stuffed things up in the windows above, and Nico. Yeah, I know. Yeah, no one's ever noticed. Most people think that I was actually hired by the city to fill in for Phoebe. Any other questions? Was this an interesting way to present it? Because this is how I remember it. you know, at the time, Gridspace was still just doing speech analysis. So we weren't doing speech synthesis yet. It was not until Tacotron came out that we started building Grace. And so, you know, we never built the WaveNet, nor did really anyone. But yeah, it is interesting. What's the question?
Can you describe the difference between regression and flow?
Okay, the question is, what's the difference between regression and flow? So there's a couple ways we can look at it. One way to look at it is a classification problem, whether it's regression or sorry, a simple prediction model, whether it's regression or classification, it's typically targeting a fairly low dimensional output space. So you might have, you know, a small set of classes with a softmax loss that you're doing as a classification problem, or a relatively small dimensional space that you're trying to regress. So Rn, for where n is not too big. As you get to the point where you have, let's say, a megapixel image like ImageNet, where you are trying to maybe predict from, let's say, there's, you know, a million different pixel values by a million different pixels. So you have this very high dimensional output space. So you could try to treat this as a million dimensional classification problem, but you're starting to the point where that's like a relatively hard thing to do in one shot. And so, you know, a flow-based model like Glow, the idea was you essentially have a one-dimensional convolution that is invertible, that allows you to just turn one input into one input into an output and one output into an input. What makes it a flow-based model is that flow, when not turbulent, is reversible, and so there was this focus on reversibility. The contrast with diffusion models, you tend to, you know, choose a process that is not necessarily typically reversible. But there, all those different models, the idea is that you're iterating, but one iteration might adjust all the pixels in one go. And that's valuable because you're doing a very simple operation across the whole pixel plane or across the sample space that is a lot more economical than trying to independently predict each pixel apart from the others, right? And so just like an RNN, where you have some sort of reusable unit that, you know, it takes advantage of some sort of symmetry in the data, flow and diffusion-based models or in GANs are all trying to predict a process that is more efficient for the space that it's generating than just doing one regression or one classification. All right, well, thanks everybody. Up tomorrow is going to be Lokman talking about Tacotron. Thanks everybody.